Hi, I am Shayantan Sen. I am currently a graduate student at Indian Statistical Institute. Today, I will talk about our work on exploring the gap between tolerant and non-tolerant distribution testing. This is a joint work with Saurabh Chakrabarti, Eldar Fisher, Arijit Ghosh, and Gopinath Misra. Let's start with the notion of probability distributions. So here we are considering discrete distributions which are defined over a set n. So here our distribution D is nothing but a non-negative function whose masses on all entries sum up to 1. So this is an example of a probability distribution. So once we have this notion of probability distribution, we now formally define the notion of distribution property. So a distribution property is nothing but a collection of distributions that are defined over the same support set n. So once we have this notion of distribution property, we can characterize distributions into several different categories. So in this work, we'll in particular consider the notion of label invariant distribution property. So a property P is label invariant if we take any distribution from D from the property. And suppose we consider the elements of the probabilities of this distribution D. So this is a multiset. Now, if this multiset determines whether a particular distribution is in the property or not, we say this property P is label invariant. So in a sense, the labels of the support set does not determine whether a distribution D is in the property or not. So this notion is formally captured in this definition. So several well-studied distribution properties are actually label invariant. For example, the uniformity property, or consider the collection of all distributions whose support size is at most n, or the entropy property. Now, on the other side, we also have this notion of non-label invariant property. For example, monotonicity property is not a label invariant property. To see why, consider distribution D which is monotone decreasing. And suppose this distribution is also not uniform. Now, if we permute the support of this distribution, so it may so happen that a probability whose probability mass is small may appear in the index 1. In that case, there are other elements whose probability mass is larger than this element at the index 1, and this distribution is not monotone decreasing. So under permutation of these labels, monotonicity property is not a label invariant property. Now once we have these notions of distributions and distribution properties, the crucial question is how do we access these distributions? So in this talk, we'll assume that these distributions are provided to us via an oracle. So think of this oracle as a black box where there is a red button outside this black box. So we push this button and this oracle provides us with an IID sample. So every time we push this button, so we get some samples according to their probability mass on D, and based upon these samples, we'll decide whether a distribution is in the property or not. Now, of course, here the goal is we need to take samples as few as possible. So the goal is to minimize the sample complexity. Okay. Now we are ready to formally define the notion of property testing of distributions. So suppose P is a property. The goal here is to design an algorithm A such that If we can access an unknown distribution D via an IID samples and we have two parameters epsilon 1 and epsilon 2, this algorithm A will say yes if D is epsilon 1 close to P, or say no if D is epsilon 2 far from P, with high probability, say at least 2/3. Now once we say D is epsilon 1 close or epsilon 2 far, now the question is, what do we mean by this close and farness? Here we say a distribution D is epsilon 1 close to this property if the minimum distance of D from all distributions in P is at most epsilon 1, where we are considering these distances in L1 distance. Similarly, we can also define the notion of epsilon 2 far. Now, note that if we set this parameter epsilon 1 to 0, this problem reduces to distinguishing the case that D is in the property or D is epsilon 2 far from this property. So these type of questions are called non-tolerant testing, and the associated tester is called non-tolerant tester. Also, for the case where epsilon 1 is non-zero, we call this problem non-tolerant testing, and the associated algorithm is called tolerant tester. Okay. Now it is clear that tolerant testing is harder than the non-tolerant testing. And there is no general recipe known by which we can convert a non-tolerant tester to a tolerant tester. So the first problem that we study in this work is as follows. Suppose we have a non-tolerant tester for a property P. Can we design a procedure by which we can design a tolerant tester from P? Okay, so this is the first problem that we will study in this work. Now, once we are considering these problems, whether a distribution is close or far from a property, so another possible approach is via learning. So suppose we have this unknown distribution D, and if somehow we can learn this distribution, that is produce a distribution which is close enough to this original distribution D, then we can actually test this property with this newly constructed distribution. Okay, so this method is called testing via learn. So formally, if we have IID samples from an unknown distribution D, our goal is to construct a distribution D tilde such that the L1 distance between D and D tilde is small. Now, as before, our goal is to minimize the number of samples that is required to construct such a distribution D tilde. So being a central problem, this has been investigated before, and for the case when a distribution D is defined over a set N, it is known that we need order n by epsilon 1 square many samples to construct such a closed distribution D tilde. Now this is possible when we know this support of this unknown set, unknown distribution D. Now what happens when this distribution D has very small mass outside a particular set S in its support? So in that case, can we somehow learn this distribution which takes number of samples that is significantly smaller than n by epsilon square? Can we design such algorithm? So this is the second problem that we will pursue. Namely, we want to learn a distribution when the support of D is unknown, and we want to design an algorithm that takes as few samples as possible. Okay. So these are these two problems that we'll study. So let us now go to our result. So our first result is a general recipe for constructing tolerant testers from non-tolerant testers for label invariant distribution properties. So here we show that we can design a tolerant tester from a non-tolerant tester with at most quadratic blow up in the number of samples. So if the non-tolerant tester requires q many samples, then our tolerant tester will require at most q square many samples. And surprisingly, our tolerant tester does not use the non-tolerant tester. It is sufficient that such a non-tolerant tester exists. And in a sense, this actually gives us a general recipe to construct tolerant testers from their non-tolerant counterparts for label invariant distribution properties. Now, this is an upper bound result. So, can we give some lower bound results for testing? So, for these results, we need two definitions. So, the first one being the definition of non-concentrated distributions. So a distribution is called non-concentrated if its probability mass is well spread across its support. So formally, if we take any set X whose size is sufficiently large, the probability mass of this distribution D over this set will be at least some threshold. And the property will be called non-concentrated if only non-concentrated distributions satisfies me. So on the other hand, we also have this notion of concentrated distributions. So a distribution D will be said concentrated if there is a set S such that the probability mass of D is almost concentrated over the set S. Namely, there is few mass outside this set S over its support. And as in the case for non-concentrated distributions, a distribution property is called concentrated if only concentrated distribution satisfies these properties. So in this setting, we show that in order to non-tolerantly test any non-concentrated properties, we need at least square root n many samples. So this proof uses ideas from uniformity testing lower bound, although we need several new ideas for the proof to go through. Now this result is about non-tolerant testing. Can we say something about the tolerant counterpart? So we show that for the case of Leben invariant non-concentrated property, tolerant testing requires at least n to the power 1 minus little of 1 samples. And the proof follows the low frequency blindness theorem of Valiant. So this is our upper and lower bounds regarding our first problem. So let us have a brief overview of our tolerant tester. Just to keep everybody on the same page, here we want to design a tolerant tester which uses at most quadratic many samples compared to the non-tolerant tester. So our tester has two phases, sampling phase and testing phase. And the main idea for sampling phase is to correctly estimate the probability masses of all high elements of the unknown distribution. So by high elements, I mean that all elements whose probability mass is at least some threshold. So formally, if the non-tolerant sample complexity of this property is Q, an element is called high element if its mass is at least 1 over Q square. So we want to correctly estimate the masses of such elements. So in order to achieve this, we first take a set of samples with sufficient size, and with high probability we know that all such high elements will appear in this set W. Now, to estimate the probability masses of these high elements, we take another set of samples, okay, also with same size O tilde Q square. So these are the two sets of samples that we will take in our tolerant tester. We do not need any other samples. So the sample complexity of our tester is O tilde Q square. So this completes our sampling phase. So let us now move on to the testing phase. So in the testing phase, we design a distribution D tilde from the estimated masses of the elements that we obtain from the sampling phase. Now once we have this distribution D tilde, we test if there is any distribution D1 in the property such that D1 and D tilde are close, and also the high mass elements of D1 are contained within the first set of samples W. So if such distribution D1 exists in the property, we say that this unknown distribution D is close to this property, and otherwise we say that this unknown distribution D is far from the property. So this is all about our tolerant tester. So this has two phases, and it seems quite surprising why does this even work, right? So let us have a brief discussion on that. So the main insight here is that if the sample complexity of the non-tolerant tester is Q, it is sufficient that we correctly estimate the probability masses of the high mass elements. That is, elements whose probability mass is at least 1 over Q square. And just to reiterate, our tolerant tester does not use non-tolerant tester. In fact, we just need an upper bound on the query complexity of the non-tolerant tester. Now, in the case of testing phase, we actually test if there is any distribution D1 in the property that satisfies some certain properties. If this property is large and it contains several distributions, testing whether such a distribution exists may take large time. Now, can we do any better? So it turns out that indeed we can. For linear properties, that is, properties which can be expressed as a feasible solution to a set of linear inequalities, we can redesign our tolerant tester, which runs in polynomial time, keeping the sample complexity same as before. So this works for linear properties like uniformity. Okay, this completes our discussion over problem 1. So let's move on to our problem 2. So here we show that if D is a concentrated distribution, that is almost all the masses of D is over a particular set S, in order to construct a distribution D dash which is close to D, we need only O tilde S many samples. And we are assuming that this set S is unknown to us. So our designed algorithm for learning this method is more general. It actually works even when we do not know the size of this set S. Okay, so we'll now proceed to describe this algorithm. Okay, so we'll give a brief overview of that. Just to reiterate, we want to output a distribution D dash which is close to this distribution D, which is concentrated over this unknown set S, whose size is also unknown to us. Okay, so for this purpose, we will actually use a result of valiant and valiant, which states as for an unknown distribution du and a known distribution dk, which are defined over a set S. In order to distinguish whether these two distributions are close or far, we need only S by log S many samples. So we'll use this result in our algorithm. So at the very beginning, we make an initial guess. We start with S being 1 and we take many samples and construct a distribution ds, and now we test whether this unknown distribution d is close to this constructed distribution ds by using the result of valiant and valiant. If these two distributions are close, we accept, and otherwise we double the value of s and repeat this procedure. So here the idea is we'll take enough samples so that we can learn the distribution supported over this unknown set S. Now it may so happen that our algorithm does not output accept even when S becomes more than 2n. So in that case, our algorithm will report failure. But in our proof, we show that the probability of reporting a failure is very small. So our learning algorithm is correct with sufficient probability. Okay, so this completes the overview of our learning algorithm. Now let us briefly see some open questions. So the first open question being, so in this work we started label invariant properties and tested given a non-tolerant tester, we constructed a tolerant tester with at most quadratic blow up in sample complexity. So can we design such a tester for non-label invariant properties? Also, our constructive tester works for linear properties, but for properties like convexities, like entropy, which are actually convex property, so can we design such efficient tester? The final question being, so can we improve our lower bound for tolerant testing from n to the power 1 minus 12 of 1 to n by log n? Thank you.